All right, in this video, we're going to talk about 6.5 in our book, where we learn about the average value of a function. It's another application of integration. And it's kind of a nice section, a pretty short section. This might be one of the rare cases where I just have a single video that covers the entire section. So what I want to do is give a quick introduction that kind of motivates the formula that we'll use to answer questions like the one you see here, where you're asked to find the average value of this function, f of x equals x cubed, from x equals 1 to x equals 3. So when we talk about the average value of something, it's probably something you've seen in a discrete case. So for example, if you're taking a class and you've had 4 quizzes, and on the first quiz you got a 90, and on the second quiz you got a 70, and then you got an 80, and on the last quiz you got a 60, I don't know, something like that. And I asked you to figure out your average quiz grade. Well, what you do is you just add up however many observations you have, the 4 of them in this case, and then divide by that number of observations, so 4. So 90 plus 70 plus 80 plus 60 ends up giving me 300, and 300 divided by 4 gives me 75. So if I had to figure out the average of these 4 observations, well, I'd sum them all up and divide by 4. And that idea is what we're going to be doing in this section. However, we're not going to add up 4 observations. We're going to kind of find the average height of a function over some given interval. So for example, if I were given the function f of x equals x cubed, and I were asked to figure out the average value of this function from x equals 1 to x equals 3, well, a geometric interpretation of what we're doing is, here's the graph of f of x equals x cubed, and we know that the height of this function when x equals 1 is at 1, and the height of this function when x equals 3 is at 27, because 1 cubed is 1 and 3 cubed is 27. So what I want to know is, what is the average height over this interval? The height's changing throughout this interval, right? It goes from 1 all the way up to 27, and if I'm somewhere in the middle, the height is somewhere in the middle. But what is the average height in this region? Well, if we had a discrete number of cases, we could just add up each of those different values and divide by how many we have. We're going to do something kind of similar, except we don't have a discrete number of values in here. We kind of have infinitely many different heights in here that we need to add up. And then we sort of need to divide by the infinitely many that we have. And that sounds really challenging, but it's not really that bad. To calculate the average value of a function, which is typically denoted f and then ave in the subscript, the first thing we have to do is something that's kind of analogous to adding up all of the different heights. Well, the height of the function is just the f of x value. And if we have to add up the infinitely many heights that we have on a given interval, 1 to 3 in this case, well, informally, you can just think about that as integrating over that integral. So from a to b, or in this case, from 1 to 3. But that doesn't give you the average value, just like adding up 90 plus 70 plus 80 plus 60 doesn't give you the average over here. After you add up those values, you got to divide by how many you have. And you're like, well, how are you going to divide by how many you have over here? There's infinitely many heights in between 1 and 3. Instead of thinking about how many you have, think about the length of that interval. Well, the length of that interval is just 2, right? 3 minus 1. Or more generally, the length of that interval is just b minus a. So all I have to do is divide this thing by b minus a. Instead of dividing by b minus a, we multiply by 1 over b minus a. Taking this integral, which you can kind of informally think of as the infinitely many heights that my function takes on between these 2 points a and b, and dividing it by the length of the interval, which is b minus a. So to divide by b minus a, I can also multiply by 1 over b minus a. And then we're done. This is the formula that we'll use to figure out the average value of our function. It's one of the formulas that I'd prefer to not give you on tests and quizzes, because I think there's some intuition there. If you already had this intuition here for how to figure out the average quiz score, the average of a discrete number of values, then this kind of follows naturally. I'm going to add up all the different heights, which is kind of what you can think of from these symbols, and divide by how many I have. How many I have is just the length of the interval. So let's see it in action. If I were trying to find the average value of this function, f of x equals x cubed from 1 to 3, all I would have to do is integrate x cubed from 1 to 3. So I got the integral from 1 to 3 of x cubed dx, but then make sure to divide that by the length. In other words, multiply by 1 over 3 minus 1. If I simplify a little bit, that's a 1/2 out in front. The antiderivative of x cubed is 1/4 x to the 4th power, and 1/4 x to the 4th power is what I'd have to evaluate from 1 to 3. Now it's just a matter of plugging in some numbers. So I have this 1/2 times 3 to the 4th power. Well, 3 squared is 9, and 9 squared is 81. So 3 to the 4th must be 81. And 1 to the 4th is just 1. So 1 times 1/4 is just 1/4. I got 81 fourths minus 1/4. So I got 80 fourths, in other words, 20. And 20 times 1/2 gives me 10. The average value of this function from 1 to 3 is 10. You're like, wow, this class has been really hard, and now all of a sudden this is really easy. This almost feels too easy. Like, what's the catch here? Well, the catch is I could change the function, I don't have to choose x cubed here. I could choose something else here, and then it might be harder to take an antiderivative. And you're like, yeah, but that's just the evaluation theorem. Like, that's stuff we learned a long time ago. That's nothing new there. I mean, sure, I guess you could throw in u substitutions and integration by parts within these problems, but that's no new stuff. That's just testing stuff that I learned earlier in the class. And that's all completely true. The only other thing that I want to add is there's a somewhat useful theorem that comes out of this, and it's called the mean value theorem for integrals. And it's a very intuitive theorem. All it says is that if you have a continuous function like we do here, so it doesn't work if your function jumps around, but f of x equals x cubed is continuous on this interval from 1 to 3, so I can apply this thing called the mean value theorem for integrals, then your function must take on this height at some point in the interval. So 10, let's see, would be somewhere in here in my picture. And sure enough, there is some point between 1 and 3 that the height of my function is exactly 10. The way you can write that mathematically is like this. And this might look kind of complicated if you read it, but it's really not that bad. It's just saying that if our function is continuous, then there must be some x value that's in that interval. So there must be some x value between 1 and 3 in this case, so that the height at that x value is the same as the average value that you just calculated. And there's lots of different ways you can prove this. You can prove this like a typical mathematical proof, but I'm kind of inclined to just show you a picture and be like, hey, doesn't this make sense? And this is the picture right here, right? If you think about the integral from a to b of some function as the area underneath the curve, so this area that's shaded in blue right here. The claim is that this line, this f average, is going to intersect with my curve at least one point in between a and b here. And think about what it would mean if it didn't. If those two things didn't intersect, then this pink line right here would be further down than the curve ever gets in this interval. But that wouldn't make sense, right? In order for this height to represent the average height over this interval of this curve, we can kind of make a geometric argument that the area underneath the blue thing is the exact same as the area of this rectangle right here. So think about it like this is liquid, right? Underneath this blue curve is a bunch of water here. And what I'm doing is I'm pouring this water into some huge cup, and I'm seeing how far that cup would fill up. It would fill up to this pink line right here. This pink line couldn't possibly be lower than the curve ever gets in this interval, because then I'd be missing a whole bunch of water. And this pink line couldn't possibly be higher than the curve ever gets in this interval, because then I'd have way too much water in the cup. In order for the area of this rectangle to be the same as the area underneath this curve, it must be the case that the height of the rectangle, informally speaking, is kind of in between the maximum and the minimum values of this function. And therefore the function must intersect with this pink line, so there must be an x value in between a and b, so that the height at that x value is equal to f average. For me, this picture is better than any proof that I could read about this thing. I can kind of think about this picture in my mind and be like, yeah, that makes sense. It would have to be. That's the mean value theorem for integrals. One last thing I want to say before I end this video is it's hard to test the mean value theorem for integrals, but there is a question that you can ask a student as like a part 2 to these questions that kind of makes sure that the student understands this mean value theorem for integrals. And really the connection between this and the mean value theorem for integrals is that the mean value theorem for integrals just guarantees that such a c exists. It guarantees that I could ask this question as long as my function is continuous on the interval from 1 to 3. And you're like, all right, so how do I actually solve this thing? Well, I got to figure out what c is equal to, so that if I take c and put it into this function, so what would happen if I put c into this function f of x equals x cubed? Well, f of c would be equal to c cubed. And I'm trying to figure out what c would have to be equal to in order for that to be equal to f average. Well, f average is something I calculated a minute ago to be 10. So all I got to do is solve for c so that c cubed is equal to 10. How do you solve this equation? We'll just take the cubed root of both sides of the equation, and you get that c is the cubed root of 10. I don't know that this exercise really helps the student understand the mean value theorem for integrals. It's really the existence of an answer that comes from the mean value theorem for integrals, but they get tacked on to questions in this section. Not every question has this tacked on, but some of them do. But what you'll see in this section is you'll just be asked to find the average value of some function between 2 points. And ideally, you'd understand this enough that it would be less memorizing a formula and more kind of understanding it. But the calculus that you do really isn't all that new. It's just an antiderivative multiplied by some constant. And you solve that and you get an answer. And then sometimes there's this second step where you have to take your function and evaluate it at this constant c and set that equal to the answer you got in part 1 and then solve for c. And what you'll see is this value of c lies in the interval that I was talking about between 1 and 3. The cube root of 10 is some number between 1 and 3. I don't know exactly what it is, but I know that it's a little bit bigger than 2 because the cube root of 8 equals 2. but I know that it's less than 3 for sure because the cubed root of 27 equals 3. So it must be some number in between 2 and 3, which is approximately where it's pictured over here on my graph. That's all I have for this entire section. I know it's kind of short and it feels like there should be more information, but it's really not. So I guess I'll end this video here.